Hello and welcome. On behalf of the Center for Occupational and Environmental Health, I would like to welcome you to our webinar, Lithium, a Novel Occupational Hazard in Electrical Vehicle Battery Production and Life Cycle, presented by Dr. James Craner and Matthew Lee. Before we get started, just a few housekeeping items. You'll be muted during this presentation. If you would like to ask a question, please enter it into the online chat or Q&A. At the completion of the presentation, the presenters are going to spend about 5 to 10 minutes answering all of your questions. You're welcome to enter questions throughout the webinar as your questions arise, and we'll make sure to cover them at the end. One continuing education contact hour is available for this webinar for a fee of $30. If you wish to obtain credit, there's an additional registration link online at coeh.berkeley.edu. After completing the evaluation for the webinar, you'll be emailed a PDF of your certificate of completion within 1 week. After today, this webinar will be hosted on YouTube, and a link will be provided to you via email. This webinar is also being live streamed on Facebook. At this time, I'm pleased to welcome our presenters, Dr. James Craner and Matthew Lee. Dr. Craner is an occupational and environmental medicine physician in private practice who serves as a corporate medical director for Tesla, Inc. He has 24 years experience in clinical and consultative practice in the diagnosis, treatment, and prevention of occupational and environmental diseases, with extensive experience in medical surveillance and compliance program development for hazardous, highly regulated industries. He serves as assistant clinical professor in the UCSF School of Medicine and is a member of the COEH Advisory Board representing Nevada. Matthew Lee is the Senior Manager for Industrial Hygiene and Occupational Health for Tesla, Inc. Mr. Lee leads Tesla's global strategy and initiatives related to worker health for automotive, EV battery, and solar products, manufacturing, and service. He has over 10 years of professional experience leading teams of health and safety professionals and managing global workplace safety and health programs. At this time, I'm happy to introduce our speakers. Enjoy the webinar.
Thank you, Michelle. Good morning or good afternoon, everybody. Today, we're going to try to cover 4 general areas. One is understanding the source of lithium and how it's used, particularly how it is extracted and formulated and incorporated into electric vehicle batteries. Second, the health effects and medical surveillance, understanding the known human health effects of lithium and its pharmacological applications, and the extent to which this goes toward understanding it as an occupational hazard. Third, industrial hygiene, challenges and strategies for measuring and controlling lithium in extraction, battery manufacturing, and recycling. And finally, the life cycle, how leaders in the EV industry are approaching product stewardship, and in particular, how recycling of materials will be integrated into best practices for health and safety. As a disclosure, first of all, the opinions and information that we are presenting today are those of ourselves and not necessarily those of Tesla Incorporated. And in full disclosure, not only do we both work for Tesla, I personally am also a customer of 2 electric vehicles, pictured here behind my son. One is a Tesla, one is a Leaf. And so my interest in batteries is not just professional, it's also personal. Demand for lithium is increasing rapidly as production and usage of EVs increases exponentially, as shown on the upper right chart. With increasing demand has come commensurate increases in price, and this trend is expected to continue. Not all lithium is used in electric vehicles, as the pie chart from 2015 demonstrates. However, the proportion of lithium used for batteries is expected to dominate. Currently, 46% of lithium production goes toward batteries, according to the Lithium Investing News as of February 2018. Lithium reserves are located in a few geographic areas that are now being actively developed. The largest reserves and the projected major source of lithium is located in South America in the desert area between Chile, Argentina, and Bolivia, commonly known as the Lithium Triangle. The Atacama Salt Flat in Chile currently generates approximately half the revenue for Sociedad Química y Minera de Chile, a New York Stock Exchange traded top international producer of lithium and other minerals. Right now, however, Australia is the world's leading producer of lithium, and China is rapidly filling the #3 position. The United States, currently ranked approximately 8th, presently has one active mine located in central Nevada, but there are many others under active development or exploration, and Canada is also developing mines in northern Quebec. Most of the lithium is mined either from rock, such as spodumene, a mineral consisting of lithium aluminum inosilicate, the form of which predominantly comes from Australia and Quebec, or from salt brines, which together with other minerals are the principal source of lithium in South America and in the aforementioned mines in Clayton Valley of central Nevada. The principal forms of lithium for utilization in battery cathodes are lithium carbonate and lithium hydroxide. On the left is a picture of a lithium brine from South America, and the schematic on the right side shows an example of the steps that are needed to process raw materials and refine it into EV battery grade lithium. These are some of the areas where occupational exposure to lithium can occur. Why is lithium so important to batteries? Recall that lithium is element #3 in the first column, or the alkali metals, on the periodic table. It is very reactive and rarely found in its elemental form. You can recall your chemistry from high school or college that lithium has 1 electron in its p orbital, which it loses to form a lithium cation very readily. Lithium has higher energy density than most available material, and it's also very light. There are a variety of cathode formulations that involve adding lithium and other metals, including nickel, cobalt, manganese, aluminum, iron phosphate, and a number of other elements. It's the addition of these other metals that impacts safety, specific energy, specific power, and lifespan, as well as the cost, which is represented in the spiderweb diagram on the upper right, in this case for the material known as NMC. Most EV batteries today are either variants of NMC or NMA, with the composition described here. But this is where the technology is differentiated by manufacturer and an area that is rapidly undergoing change. Lithium represents the largest molar fraction of the cathode cation, but because its atomic weight is so low, by weight, it represents a relatively small fraction of the cathode material. But the cathode material as a whole is the major cost fraction of battery production. A brief description of how it works. The EV battery is comprised of a cathode or positive electrode, an anode or negative electrode, which is usually comprised of graphite, an electrolyte that conducts electrons, a separator diaphragm that allows only electrons to pass through it, a connection or leads through which the current flows, and an insulator jacket and gaskets that insulate the voltage generated in the cell from the exterior. Electrolytes are non-aqueous liquids, or in newer forms, solid polymers. This liquid or solid is a solvent or material that contains lithium and any number of anions, including phosphorus, fluorine, boron, or carbon. Electrolyte decomposition and highly exothermic side reactions in the lithium-ion batteries can create an effect known as thermal runaway. Thus, the selection of an electrolyte often involves a trade-off between flammability and electrochemical performance. Both electrodes basically are comprised of a 3-dimensional molecular structure that allows lithium ions to move in and out of their structures with a process called insertion and extraction, sometimes chemically known as intercalation and deintercalation, respectively. During discharge, the positive lithium ions move from the anode to the cathode, forming a lithium compound through the electrolyte, while the electrons flow through the external circuit in the same direction. Conversely, when the cell is charging, the reverse occurs, with the lithium ions and electrons moving back into the negative electrode into a higher net energy state. As shown here in the upper right, there are 2 main formats for EV battery cells: prismatic, as shown on the left, and cylindrical, as shown on the right. They're both comprised of layers sandwiched or rolled together. The finished products come in various sizes that are named for their dimensions. For example, a 18650 cylindrical battery is 18 millimeters wide and 65 millimeters long. These cells are then assembled into battery packs, and Tesla's Gigafactory 1, located near Reno, Nevada, where I'm based, is where Tesla manufactures its Model 3 batteries. The battery is the heaviest component in the electric vehicle, And in this respect, the trade-off between weight and energy density is where the technology continues to advance and be differentiated by manufacturer. Now I'm going to turn to talk about the occupational uses and monitoring of lithium. As part of the process of developing a chemical health risk management best practices program for the Tesla Gigafactory, I conducted a detailed literature search for occupational lithium exposure and related topics to identify available resources and incorporate them into practice. The two tables that I present here summarize my searches from Embase and PubMed respectively. A few key points. Number one, as you can see here, lithium is a very, very large topic, but when it is combined with terms like occupational exposure, medical surveillance, or industrial hygiene, there are virtually no references. Those references are not specifically related to lithium. Google searches and Google Scholar searches similarly yield almost no information about this topic, with only one textbook actually covering lithium and having no mentions of occupational lithium exposure. The articles that have been identified about lithium and health effects have focused primarily on environmental lithium exposure from drinking water contamination. Consequently, and as the industrial hygiene portion of this section of this presentation will describe, regulatory information on lithium is similarly lacking. So as it turns out, most of the information about lithium comes from its non-occupational sources. Lithium is a non-essential element in humans. It's commonly found in soil, plants such as grains and vegetables, and animal-based products, particularly dairy foods, and in the water supply. A bit of interesting history. In the 1880s, lithium salts were commonly added to elixirs, tonics, and refreshment beverages to make them more appealing. In the mid-20th century, doctors prescribed lithium salts as a substitute for sodium chloride or table salt to prevent or treat hypertension and heart disease. The popular caffeine-free soft drink 7-Up was originally formulated and marketed as lithiated lemon soda beginning in 1929, with lithium citrate as its proprietary ingredient. These practices continued up until approximately 1950, when the practice ceased after numerous cases of severe kidney and neurological toxicity were reported. Lithium's principal modern usage began in or around 1970, when the US Food and Drug Administration approved lithium carbonate for the treatment of mania as part of bipolar disorder, formerly known as manic depressive disorder. Since that time, lithium, primarily as lithium carbonate, has become the standard of care for primary and secondary prevention of bipolar disorder, a highly prevalent psychiatric disease throughout the world. Knowledge of lithium's metabolism, distribution, and kinetics was largely extrapolated from animal experiments and anecdotal human findings that have been reported in over 5,000 publications over the past 40 years, all of which showed up in the literature search I described. This includes reports from accidental and intentional or suicidal ingestion. The toxicology and pharmacology of lithium is very complex, and this slide attempts to summarize some of the key findings. Lithium is absorbed efficiently from the gastrointestinal tract and reaches peak plasma concentrations in 1 to 2 hours. Its absorption efficiency via inhalation, which is the primary route of exposure, both in mining of lithium hydroxide or carbonate or oxides, as well as respirable lithium metal oxides, is unknown. Secondary ingestion, swallowing of respirable and larger non-respirable forms of lithium-containing particulate can occur from hand-to-mouth contact, just as it can for any other workplace contaminant, during eating, drinking, or smoking activities if proper industrial hygiene, practices are not effectively implemented. A few key factors about lithium's metabolism. First, like sodium, lithium crosses all biologically active membranes and is uniformly distributed in body fluids. Second, it is neither transformed nor detoxified or found bound to proteins at therapeutic levels in the body. Third, it is very rapidly excreted predominantly by the kidneys. These aspects of the toxicology and pharmacology are directly relevant to several aspects of occupational exposure risk. First, and as indicated on the dose response section of this slide, despite its relatively short half-life in blood, Once a steady state in the blood is achieved, lithium may take as long as another 24 hours to act on the brain, where its half-life is estimated to be 30 to 36 hours. While lithium requires repeated, regular dosing to be effective over months of years of usage, it does not lose its psychiatric or target effectiveness, nor does its toxicity wane. That is, people do not become tolerant of lithium. Second, despite the long-standing empirical recognition of lithium's efficacy, the biomolecular mechanism by which lithium stabilizes mood or causes toxicity in humans remains largely unknown. An important point is that although many theories or hypotheses about its effect on neurotransmitters have been proffered, countless experimental studies in laboratory rodents over the past 3 decades have not produced any consistent, reliable information for corroborating these theories, targeting lithium's effect on mood or reducing its toxicity for humans. Third, lithium has a very narrow therapeutic index. A therapeutic index is a comparison of the amount of a therapeutic agent that causes the therapeutic effect to the amount that causes toxicity. There is a relatively small range of dosage or measurable concentrations in body fluid, such as blood, necessary to produce the therapeutic effects, above which adverse effects occur. In addition, lithium toxicity is highly influenced by drug interactions. This table summarizes the major classes of widely prescribed medications, including for conditions such as high blood pressure and a variety of causes of musculoskeletal and other forms of pain that are for many highly prevalent conditions, which are known to increase blood lithium concentrations and commensurately increase the risk of acute lithium toxicity. These interactions have bearing on how workers who may be exposed to lithium may be affected as a result of underlying medical conditions and medications prescribed for them, as well as dietary and lifestyle behaviors, including alcohol consumption. This table summarizes the acute toxicity characteristics of lithium as a medication. The most common side effects are polydipsia and polyuria, which means excessive thirst and excessive urination related to the effects of lithium on the kidneys, dry mouth, weight gain, fatigue, drowsiness, decreased libido or sex drive, tremor, headache, nausea, vomiting, and diarrhea. These acute effects, which are often referred to as side effects, occur in up to 75% of people, but the frequency, order, quantity, multiplicity, and combination remains poorly characterized. In fact, the natural history of lithium side effects has been described in one recent review article as rather scattered. As the amount in the body increases, acute toxicity can progress to chronic and potentially irreversible toxicity, manifested by worsening neurological effects, kidney failure, mental and psychiatric effects ranging from confusion and drowsiness all the way up to truncal ataxia and choreathetoid movements, which are basically kind of bizarre postural movements that are uncontrolled, renal failure, and electrolyte changes with or without arrhythmias. The target organs that lithium can affect are many, and I'm going to touch on a few of the important ones, which are bold-faced. The first is diabetes insipidus. This is an electrolyte disorder that, like the term diabetes mellitus, causes excessive urinary water loss, called polyuria, and subsequent excessive thirst, called polydipsia, to replace these losses. Lithium acts by blocking the effect of ADH, a hormone secreted by the pituitary gland that acts to stimulate thirst and ultimately control water balance and plasma osmolality, or total electrolyte and other minerals in the blood, thus basically controlling the equilibrium state and homeostasis in the body. Diabetes insipidus develops in 30 to 40% of people taking lithium within a few years. And by the time people have taken lithium for more than 10 to 15 years, it approaches 100%. Depending on how severe and the extent to which the kidneys are compensated, diabetes insipidus can lead to volume overload or depletion, causing a variety of constitutional and potentially disabling symptoms, hyponatremia, and a metabolic acidosis, which can lead to very significant adverse health effects. Lithium also has a significant effect on the thyroid, affecting as many as up to 25% of people taking the medication over time. Hypothyroidism in young people can produce lethargy, weight gain, insomnia, dry skin, hoarseness, diminished concentration, and other global or constitutional effects. Hypercalcemia can be asymptomatic and even at relatively low concentrations can cause systemic symptoms, which can overlap with those of lithium toxicity, and at high concentrations can produce a potentially fatal heart arrhythmia. There are rare and very significant cerebellar syndromes that can be caused. Psychiatric effects of lithium in people who don't take mania or don't have mania and don't have depression are unknown, just like I talked about with the effects of 7-Up and those therapeutic elixirs. So it's uncertain what effect lithium has on the mental state of people who don't have these psychiatric disorders. And finally, lithium is recognized as a potential teratogen with a wide variety of opinions as to its teratogenic effect. Guidelines for bipolar treatment disorder for women who are planning to become pregnant or early in pregnancy advise discontinuation of lithium during at least the first trimester. So what are the medical surveillance strategies that are needed for people who handle lithium? Well, as I described, there's essentially nothing in the medical or industrial hygiene literature on this topic. And so part of our mission is to really set up best practices and understanding that medical surveillance is the process of identifying, quantifying, and removing causative factors that increase the risk of occupational disease or injuries. We think that this is a topic that has significance for setting how workers will be effectively protected and how companies will manage workplace exposures to lithium, either in mining, cathode production, or actual use and recycling of this product. It should be clear that lithium toxicity involves a wide range of organs and differential diagnoses, as I've explained. So the following are some considerations for developing a best practice approach to medical surveillance. First, the frequency of such evaluations needs to address medical history and risk factors. How often to evaluate workers is an important consideration that's based on the extent of exposure, level of protection, and as I described, the narrow therapeutic index, even though in this case, lithium is not being taken intentionally, but potentially getting into the body. Second, based on lithium's toxicity profile, individuals with certain medical conditions may need to be disqualified or more carefully monitored. Third, the content should include a variety of features that are summarized on this slide. It's clear that a lot of information needs to be conveyed and interpreted in evaluating whether or not and to what extent an individual is at increased risk for or affected by lithium. And finally, laboratory tests that are routinely conducted in lithium treatment for bipolar disorder include kidney function, thyroid, and calcium, probably also need to be obtained. My last slide concerns biological monitoring. Clearly, if workers are exposed to lithium on an ongoing basis and its toxicity profile is both acute and chronic, measuring internal exposure and identifying early reversible toxicity makes sense from a medical standpoint. Here again is where lithium therapy has a long-standing benchmark to apply to developing a best practice occupational biological monitoring methodology and strategy for which, as I presented, there's no published experience or guidance. The standard of care for lithium therapy is a blood lithium test. This is routinely used to measure the state of lithium therapy and to determine whether and to what extent toxicity is occurring. As I mentioned and described, lithium has a very narrow therapeutic window, and this dictates the frequency of monitoring. The target blood lithium level varies depending on the indication, specifically whether it's mood stabilization or prevention of mood alteration. And as this diagram at the upper right shows, there's a great amount of variability in how to prescribe lithium. For biological monitoring, urine lithium is probably the best marker. As I mentioned, lithium is rapidly excreted from the urine, and it has a low level of detection. But there's really no research, regulations, or professional guidelines in the occupational setting. So in looking at urine lithium as a biomarker, we need to consider the lack of reference ranges, the fact that it's normally present in the diet, we have to look at creatinine adjustment, particularly because lithium actually affects how the kidneys handle creatinine and urine volume. And finally, to determine whether or not urine should be co-monitored with blood, which is already well known. So the last point I want to raise is that the approach to biological monitoring really needs to move from looking at results one at a time to really looking at aggregate trend for distribution, variability, and trends within similar exposure groups. And to this effect, our approach is to go beyond the traditional biological exposure index as an individual marker and move toward using statistics to look at aggregate indices of exposure control and aggregate safety, just like industrial hygiene. And with that, I'm going to segue and hand the talk over to Matt to talk about industrial hygiene.
Great, thanks, Jim.
And you just need to advance the slide.
Great, thanks, Jim. What Dr. Kraner had covered illustrates lithium's inherent toxicity and the opportunities for developing a best practices approach to medical surveillance and biological monitoring for lithium exposure in all facets of lithium use, whether it's mining, refining, and processing, conversion into cathode starting materials, and even recovery. We just heard how surprisingly there's little published research concerning lithium as an occupational health hazard. This situation presents an opportunity to develop best practices approach to industrial hygiene that is, one, based on established industrial hygiene principles, and two, closely integrated with the occupational medicine side, since protection of worker health is a performance-based objective. What I want to do is summarize the industrial hygiene principles and applications to lithium, primarily in the battery manufacturing industry, which then can be applied to any of these other lithium operations that Jim had mentioned during his presentation. So this slide above shows the key components of an industrial hygiene best practice, which aligns with the standard risk assessment process: hazard assessment, exposure assessment, risk characterization, and exposure controls. So occupational exposure limits, as previously discussed in the toxicology and the health effects portion of this presentation, there is a significant lack of systematically collected longitudinal medical surveillance and biological monitoring data that's available for these materials. First off, there's no established occupational exposure limit, or OEL, whether that be an OSHA PEL, an HGIH TLV, or even a NIOSH REL for lithium salts or for mixed metal oxides. That said, OELs are available for individual constituents of lithium mixed metal oxides. Aside from lithium, none of the other constituents, including nickel, is acutely toxic at low dosages, and most of the other concerns are for long-term risks such as cancer, heart, or neurological disease. This is why establishing an OEL for lithium and lithium metal oxides must consider lithium toxicity as a principal determinant based on the information that we just heard from Dr. Jim Kraner. You know, there is a tendency in industrial hygiene to rely heavily on OELs to dictate compliance. But as HGIH makes clear, TLVs and other OELs are not fine lines between safe and dangerous exposures, nor are they a relative index for toxicology or toxicology. So the traditional practice in establishing OELs is via an extrapolation of dose-response health endpoints for animal experiments. This is not considered a best practice, and in fact, the methodology is rapidly becoming obsolete. The inaccuracy, the uncertainty, and the unreliability in translation of effects observed in rodents and other animals to actual human health risks from an occupational exposure standpoint to chemicals highlights the increasing movement in toxicological research away from animal experimental methods. In addition, as was highlighted in last year's COEH webinar, in animal toxicity testing, these methods are extremely inhumane and also they're very expensive. Our best practices approach is to apply the available human health data and the principles of industrial hygiene and occupational medicine to inform exposure assessments, health-based assessments, and exposure controls, rather than simply just allow or follow an OEL and assume that it's protective. In the case for lithium, the opposite approach may be needed: a continuous objective assessment that's based on health outcomes and is conducted in a measure of effectiveness of exposure controls from an industry or a hazard-specific OEL can eventually be developed. The exposure assessment and monitoring, workers handling lithium-containing cathode materials may perform tasks that involve loading, unloading, or handling starting materials. Mining personnel may also have exposures during product refining and packing. The photo on the slide is an employee at a lithium mine in central Nevada as he bags lithium carbonate product. As you can see, there's rather crude controls and a lack of PPE that's being utilized. What I'd like to do now is take a minute to explain the exposure assessment process, starting with explaining what a qualitative assessment is. Qualitative assessment is a preliminary observational assessment where the industrial hygienist uses the information on the processes, worker tasks, and the potential exposure routes to categorize exposure potential by exposure risk. The process typically starts with defining your similar exposure groups, or your SEGs. And an SEG is essentially a defined subpopulation of workers who experience comparable exposures to one or more contaminants as a result of working in common areas or having common tasks or being in similar conditions from an industrial hygiene perspective. For employees to be considered to be part of the same SEG, sampling data collected from one individual or group should accurately represent a range of exposures for all employees within that group. Qualitative assessments are usually followed by quantitative assessments, or traditional industrial hygiene monitoring, based on where the industrial hygienist believes that there's a potential for increased exposure. With respect to the focus of this webinar, NIOSH method 7300, which is elements by inductive coupled plasma, or ICP, is ideally suited to evaluate cathode starting materials because it provides a single accurate method to simultaneously measure all, or even just one of the constituents, lithium, nickel, cobalt, manganese, and aluminum, in the same air sample. The method involves the use of standard MCE filter cassettes, IH pumps, traditional sampling train, and calibration. Now, the strategies for lithium are share similar similarities to lead, a toxic material, even with extensive regulations that continues to be a challenge to control in the workplace environment. Time-weighted average sampling is typically done for compliance purposes. Peak and ceiling samples are collected over a relatively short period of time to determine maximum exposure to a specified contaminant. Area samples are placed in the general work areas for extended work times, determine whether employees are at greatest risk of overexposure. Task sampling involves taking a personal sample over the course of a specific worker's task or job. There's also portable monitoring and surface wipe sampling. In the case of surface wipe sampling, it's utilized to determine whether a particular contaminant exists in an area or not. Lithium salts or metal oxides are not absorbed through the skin. However, surface dust sampling identifies potential sources for oral ingestion of contaminant as a possible route of exposure, and evaluates the effectiveness of ventilation, housekeeping, and other hygiene exposure controls that are in place. Sampling frequency and quantity, both our initial determination and on an ongoing basis, are important topics that should be addressed. Now on exposure controls, I wanted to briefly touch on the exposure controls from a risk management perspective. Now, based on your exposure characterization, the effective controls can be established to reduce exposure in the workplace environment. And the traditional industrial hygiene hierarchy of controls is shown here on the slide. And as with any occupational stressor, the hierarchy of controls can be utilized in the case for lithium. Obviously, the most effective method to completely mitigate exposure is via elimination or substitution. However, this is usually the most impractical, and obviously it would be certainly impractical in the case of our industrial environment with within our electric vehicle industry. The best method to reduce or completely mitigate exposure beyond substitution is via engineering controls, which entail a physical change in the workplace, such as enclosures or ventilation. Engineering controls tend to be highly effective and are not typically affected by an employee's work practices, which make them ideal. Now, the lesser effective control are those that are administrative, such as job rotation. These tend to be more dependent on the worker's training and are often more difficult to consistently reduce exposure. Now, the last and unfortunately the most used control tends to be PPE. Now, these really should be used as a last form of defense and should only be used as an interim control until more rigorous controls, such as engineering controls, can be instituted. Now, switching gears a little, in the last section of the presentation, I want to discuss the EV battery life cycle. Now, anyone concerned with economics or the environment already knows that EVs are more energy efficient, they make no noise, they don't pollute the air, they don't generate greenhouse gases, and they don't require non-renewable petrochemicals, which are energy intensive, environmentally destructive, and politically volatile. So the question that can be reasonably asked is it environmentally sustainable and cost effective to mine the lithium and other materials, process them into batteries, only to last however many years or how many miles? Now, the short answer, in my opinion, is yes, of course. topic is actually getting a lot of attention outside of the industry. A recent article by Bloomberg Businessweek on the current state of EV battery recycling advised that most of the automotive EV manufacturers have plans to repurpose spent batteries and to get some additional years out of them. But Bloomberg noted that only Tesla has a long-term plan for a full life cycle. According to this article, by 2040, more than half of the new car sales and a third of the global fleet, equal to over 550 million vehicles, will be electric. Now, by 2050, companies will have invested about 550 billion in home, industrial, and grid-scale battery storage. Obviously, the number of batteries is going to be massive. Now, on battery recycling, all these companies are currently making EVs purchase their battery cells through a battery manufacturer. There are several major battery manufacturers in the industry. The general principles of lithium-ion battery cells is the same. The cell materials and how they're assembled into packs varies widely and is always continuously evolving. Tesla is the only fully integrated EV manufacturer. The company not only builds its vehicles, but makes its own batteries directly with a major partner. The intent of this strategy is not only to improve the efficiency and reduce battery costs, but to also ensure that the product lifecycle can be controlled and effectively managed. Now, lead-acid battery recycling is a well-established process. In industrialized nations, there's a system in place to recover batteries, such that about 99% of the batteries end up being turned back into new batteries. Lead-acid batteries recycling is done primarily through high-temperature shredding and smelting operations. Now, Dr. Jim Craner has consulted with companies in this industry and can attest to the process entails significant airborne lead, noise in the work environment, which presents an occupational health, industrial hygiene, and environmental control hazard and requires the right requirements to be in place. The photo on the slide shows workers in a large US steel recycling smelter handling lead ingots. Occupational health and safety is a major focus in these industries, even with the OSHA lead standard in place and a very high level of regulatory oversight. The chemistry of EV batteries is quite different than that of lead acid batteries, as we presented earlier. Now, in the case of EV battery recycling methods, now the process flow for battery recycling is summarized in the flow diagram at the top right. This includes collection and transport, separation, chemical extraction, processing, and conversion back into cathode or other starting materials. Ultimately, the recycling process needs to be economically viable, scalable, and energy and environmentally efficient. There are several different methods for EV battery recycling that can be summarized here on the second table. Now, here comes the hard words to pronounce. Pyrometallurgical. This process is analogous to the lead acid battery smelting. It is energy intensive and it requires higher temperatures that present an increased probability of airborne lithium and other metal exposures. Lithium itself is actually recovered as a slag, which must be further refined or sold for use for other purposes, such as construction materials. Hydrometallurgical, this process requires separation of battery components into more sophisticated chemistry, but is also more energy efficient and allows for lithium salts to be directly recovered. Now, direct CO2 electrolytic separation. Now, this is theoretically the most efficient in terms of recovering cathode materials in a more directly reusable form. Now, a lot of research is now occurring to develop this method into a more commercially viable scale. All these technologies obviously have their benefits and their disadvantages. So, opportunities and challenges. The opportunities and challenges for the EV battery life cycle can be broadly categorized into four groups: the technical aspects, the economics, obviously health and safety, and industry. Health and safety, what we're focused on today in this webinar, is one aspect. The take-home point is that EH&S, or environmental health and safety professionals, really need to be part of the strategy from the onset. And that includes the points that we discussed today regarding lithium's toxicity, and requirements for medical surveillance, biological monitoring, and obviously the aspects of industrial hygiene, exposure assessment, and control. Now, Tesla is already developing and implementing a fully integrated battery recycling process that includes not just our own, but all EVs. Our objective is to close the loop on the supply process, which is consistent with our corporate mission of accelerating the world's transition to sustainable energy. Many other companies in the battery industry, automobile manufacturers and recycling companies, are developing obviously their own plans. Like any industry, there will be a variety of approaches that depend on obviously a number of different factors. So with that, that ends the industrial hygiene perspective of the webinar. I wanted to turn it over to the coordinator for any questions.
Great, wonderful. Thank you guys so much for that presentation. We do already have a question in the queue here. So this one is, what level of exposure would trigger evaluation in the event of a single occupational exposure, such as firefighters who respond to a car fire where a lithium battery was compromised and leaked?
I'll take that one if
Sure.
I'm heard. That's a really good question. And the answer is that you have to look at acute toxicity with lithium literally occurring within a period of hours to days. That would be partly why medical surveillance and baseline assessment would be so important. What would trigger it would be the probability of exposure based on the circumstances. The lithium in and of itself in a battery fire would be unlikely to be released due to a variety of physical properties. However, in other phases of operation, it's possible that lithium would come out. There are many other components to the battery that might present a hazard. Differentiating those would be very difficult due to the complex chemistry of the battery as I presented.
Great, thank you. And yes, I do want to also let everyone know that after the webinar, I'll be sending out an email with a link to watch the video again and also a link to the slides for the presentation. So we also have another question. Does your company have internal OELs? If so, what are they? At what level of action taken to reduce exposure? What level is action taken to reduce exposures? What levels of exposures occur to employees in separation and battery recycling?
Wow, that's certainly a compound question. I'll try to answer it at least initially, and then Jim, I'll turn it over to you. So our industrial hygiene program continues to grow. We're focused on following the AIHA strategy to assess and control exposures. With that, we really look beyond just simple OELs from a compliance purpose. Like I mentioned during my presentation, obviously you can rely on the ACGI TLVs, you can rely on CalOSHA, Federal OSHA PELs, or you can even rely on NIOSH RELs. But we really want to look beyond that and be able to integrate the occupational medicine side with the industrial hygiene side. So obviously that first starts with using applicable OELs, but really within Tesla to really go beyond just a traditional industrial hygiene approach, we're going to go beyond just simply looking at an OEL. So that kind of answers on a broad level. Now, I think there's a lot of components to the compound question, but irrespective of that, really our focus is to be able to characterize exposure to our workers in all different scenarios and really take a risk-based approach to industrial hygiene and occupational medicine. So Jim, I don't know if you wanted to add anything to that with respect to the questions that were asked.
Yeah, I think part of what we wanted to convey today is that realistically an OEL won't be available. Second, that using animal experiments and other somewhat outdated approaches to toxicology, as Matt presented, really is not going to be effective. We know that lithium's toxicity is not well characterized by animal studies, and basically that the human health effects are quite different than they are for other animals. And we know from an extensive amount of experience that lithium is acutely toxic. So I think what will happen is that we will, at least in our areas, address the health side and use the measurements and then try to, through a process, understand at what levels are safe and effective, rather than trying to determine safe and effective levels and then comply with them. That is out of necessity, and I think that is out of best practice, focusing on a human-centered approach to toxicology that integrates occupational medicine and industrial hygiene, which is kind of the opposite of historically how OELs have been established.
Excellent, thank you. A few more questions here. The first, how are the process and human hazards of the cobalt, nickel, and fluorine atoms in some lithium batteries formulations?
I'll take that and say that that is a very complex topic that's beyond the scope of answering here. There's a lot of widely available information, requires a lot of knowledge of chemistry. Today, I tried to give a very, very high level 40,000-foot overview of the chemistry of these batteries, but I would encourage someone to read up on that. And just to be able to say that the cathode materials, which we're focused on, is just one part of the battery. The electrolyte, the anodes, and some of the other constituents in and of themselves have a chemistry that is important, but again, not the focus today.
Great. And can you say anything about the quantitative air sampling results that you've seen in battery manufacturing and that you've measured?
So I'll take that. I mean, that's something that we're continuing to evaluate internally. So I don't want to share this data as part of this presentation, but it is something that we continue to characterize both qualitatively and quantitatively.
Great, thank you. Another question, how strong is influence in developing and or changing the production process and the workplace related exposures?
Right. So I can take this from a non-technical perspective, and Jim, you can add to it. So one thing that I will say with Tesla is we take health and safety very seriously, and EHS is integrated into the overall process. So that allows us, from an industrial hygiene perspective, from an occupational medicine perspective, to be able to influence and ensure that we have the right controls in place, mechanisms in place to reduce exposure. And that we, are effective. We're monitoring the efficacy of those controls that are in place.
Yeah, I think Matt answered that really well. Obviously, without getting into too much technical details, that's part of the reason that we're giving this webinar now, is to begin to educate and inform the world that this is a relatively novel hazard. Even though lithium has been in use in the battery industry since the early 1990s and is obviously widespread in the consumer electronics field, the sheer scale of it and the size of electric vehicle batteries, and as I showed, the demand for lithium is probably going to change that. As well as I think the environmental and life cycle costs, both from an economic and environmental standpoint. So much of the information that we use and rely upon, I think, will ultimately become the standards that become in place for everybody else. And that's why I think what we're doing is leading in the field. So obviously it's somewhat cutting edge, and we can't simply look at what everybody else is doing and say, let's just copy that, or we're required to do it. At the same time, we're trying to go develop our policies and procedures based on very well-established principles, both of occupational medicine and toxicology, as well as industrial hygiene.
Excellent. And this looks kind of a follow-up to what you were just talking about, but since EVs are increasing in popularity, do you expect to have exposure limits set by OSHA within the next several years?
That's a great question. I think if history is any indication, the OEL process, or the process to establish or change a federal OSHA PEL tends to be very long. I think we can use examples in the past, whether it's the changes to the asbestos PEL or the silica PEL, it's taken years. So while it would be great as the research continues and we're better to characterize exposure in the occupational environment for there to be an established OEL. But from my perspective as an industrial hygienist, I always want to look beyond just a simple OSHA PEL or Cal OSHA PEL, or even an established HTLV, or really any OEL, when I'm looking to characterize the risk associated with exposure in the workplace. So with that said, I would love for OSHA and other groups to continue to update and develop new OSHA PELs, but I don't foresee that happening anytime in the near future.
Excellent. And another question, would your reservations about studying lithium by traditional toxicology animal studies extend to the in vitro testing approach, Tox21?
I think the question relates to studying it in cells as opposed to in sentient animals. If my understanding is correct, I wouldn't necessarily oppose that, but I think, and the point of this presentation is that there is a plethora of information, albeit somewhat scattered, about lithium's health effects in humans that is what we should be relying on. I didn't cover today, just in the interest of time, the fact that there's potentially synergistic or multiplicative effects of, depending on the process of other materials in the work environment. But I think our most direct method is human epidemiology and essentially applying known pharmacology and pharmacotoxicity to occupational exposures. That's where I think lithium will be somewhat novel, in that it has heretofore been used essentially entirely as a medication and now potentially represents an occupational hazard. What's likely to happen, as Matt alluded to, is that if there are a few overexposure cases, they will probably lead to a very reactive regulatory approach. We'd like to avoid that. That's been the history of a lot of other materials. And that is, again, why we are being so proactive on this topic, and again, why we are trying to integrate occupational medicine and industrial hygiene together rather than taking them separately. So some entities may be doing research, but since this is a field that is largely industry driven, I think we're going to be able to focus on as much human relevant information as is possible.
Excellent. So we have another question related to health surveillance on workers in manufacturing, and if you have any recommendations for smaller garages, what they should do if they handle this type of product.
I'll take that one. Smaller garages should not be handling this product, much like lead, and that's why the lead acid battery industry, which Matt discussed for this purpose, has a system in place for systematic collection, transport, and processing of lead acid batteries. We think that ultimately the EV battery industry, at least from our perspective, will be controlled enough that when the battery's useful life is over, it won't end up in the hands of an individual in a garage trying to figure out what to do with it. I know there's YouTubers who go out and disassemble batteries for show and so forth, but on a commercial scale, it's very likely that the batteries will be handled within a system, and basically within several days or weeks, the lithium taken out of an old battery will be converted back into a new one.
Excellent. It looks like we do have a few more questions. This is great. I am so happy we had a lot of time for all these great, wonderful questions. How do you integrate workers in the process of adapting workplaces? Do you provide training and possibilities to influence changes in the production process?
Yeah, I'll take that one. It's, I mean, that sounds like it's a little bit more broad than the context of this specific webinar, but, certainly, we integrate all facets of the workforce and the workplace when we're establishing our processes in place, both from an EHS perspective and then obviously beyond an EHS perspective.
Excellent. And then we have another question. In absence of OELs, are you relying on symptomology as a reference for the effectiveness of workplace exposure controls like PPE and et cetera?
Well, that's what we discussed as a challenge. We're certainly not at that point yet, but we don't rely entirely upon symptomatology. And all medical surveillance, and for that matter, all of medicine ultimately relies clinically on a history. So part of what we rely upon is medical conditions and status and asking about symptoms, but we also rely on physical exam and potentially biological monitoring. Those are the reasons that I discussed all of those. Putting that all together into a cogent program that could be implemented is what we're currently in the process of developing and rolling out. And particularly as our end of the business evolves, that will become more prevalent. And I think it'll be a combination of essentially medical monitoring, which is a subset of medical surveillance, as well as combining biological monitoring data and industrial hygiene data to assess overall worker exposure and health effects, and make a determination, as I emphasized, on an aggregate level of what's happening, rather than, which is the traditional OSHA approach, of taking each worker one at a time and not really focusing on the overall worker population, or as Matt described, the similar exposure group.
Thank you. And as it relates, going back to the research and how it's kind of limited in the occupational exposures, are you aware of any studies underway as it relates to lithium in terms of inhalation or respiratory exposure?
I'll take that one. From a medical standpoint, in terms of occupational medicine, I'm not aware of any. There could theoretically be ones on animals, and for a variety of reasons that Matt focused on, those probably are not going to be reliable. They certainly have problems from an ethical standpoint and a cost standpoint, but I'm not aware of any on humans because this industry is so relatively inchoate in its overall development and scale. So if there are, we'd be interested to hear about them.
Great. And these questions look a little bit more about the battery, but does humidity affect battery raw materials and finished batteries?
Answer is yes.
Okay.
Yeah.
And do you guys know the half-life of a lithium battery?
I don't off the top of my head, and I think really our focus, while we did touch on EV battery technology a bit, really our focus has been more on the health, toxicological aspects, and industrial hygiene considerations.
I can comment because it was in one of the slides that assuming that a battery, I think you mean how long will a battery's life be? That remains to be seen and has a lot to do with the battery technology, but it is on the order of 10 or more years. And the first electric vehicles now out on the road, some of them have gone well beyond 10 years already. So I think it'll remain to be seen, but realistically, it's in the 10 to 20 year lifespan.
Great. And another question about exposure pathways. Are they similar during the recycling phase as the production phase? Are there special concerns as it relates to battery recycling?
I'll take a shot at that, and then Matt will probably have some comments. The three methods that Matt proposed each have different risks associated with them, and it will depend largely on the methodology that is used. Part of the life cycle strategy will be to have as least hazardous, but also as economically efficient method as possible. So the exposures will relate to whether or not high temperatures are being used and the extraction process. Recycling probably presents the most opportunity for lithium exposure as well as other metals exposures, as does the raw mining of each of those materials.
Right, and the technology continues to change, and as it changes, that'll obviously impact the exposure potential and then the subsequent exposure controls that we would need to have in place.
Wonderful. Well, thank you both so much for your time. This has been very informative. And thank you to everyone who joined us for today's webinar. Our monthly webinar series takes place on the first Wednesday of each month at 10:30 a.m. Next month, on Wednesday, September 5th, we're honored to welcome Beverly Nichols and Matthew DeAngelis, who are going to be presenting on respiratory protection in the workplace. This coincides with N95 Day, which is a NIOSH Awareness Day about respiratory protection. Details about our webinars and other upcoming events can be found on our website at cueh.berkeley.edu. So I wanted to let you guys know about a couple other things coming up this month. We have Health from the Soil Up on Thursday, August 9th in Berkeley, California. In coordination with this event, there's a free introduction webinar on Monday, August 6th on farm policy and chronic disease. How are they linked? You don't need to register from the Health from the Soil Up to attend that free webinar on Monday. We're also going to be hosting a Fundamentals of Workplace Safety course on Thursday, August 16th and 17th, and Friday, August 17th in Oakland, California. And we also just launched an online ergonomics program, and our first course, Fundamentals of Human Factors in Ergonomics, is going to be starting August 27th. All of these and more are going to be available on our website, cueh.berkeley.edu. I'll also be sending out a follow-up email from this webinar with links to the video if you wanted to watch it again. Thank you all so much for joining us, and I hope you have a wonderful day.